Hello, 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 and welcome back to Shiksha DaCosta. Today we're going to learn how to solve problems using the properties of geometric figures. As part of this lesson, you're going to learn how to plan and implement a multi-step strategy. That strategy is going to involve analytic geometry and some algebraic techniques that you should be really familiar with by now. And we're going to use all of those things to verify a geometric property. To start off, I'd like you to just on a sheet of grid paper, draw a circle and try to use a compass to do this. A compass is that instrument where you can sort of put one point down in the center of something and then use the other point to draw the circle. And by doing so, you should get a perfect circle every time. And that point, that indentation will probably remain there in the center of the circle on your paper. Once you're done that, and pause the video at any point throughout these instructions if you need a little bit more time to complete your circle or whatever. Once you're done drawing your circle, I'd like you to plot 2 points anywhere along the circumference of the circle and join those 2 points with a line. So I've chosen to put one here and one over here, and I'm going to join those 2 points with a line, and this line is called a chord. A chord is a line that joins 2 points on the circumference of a circle. Now that you've got your chord, and your chord probably looks a little bit different than mine, and that's okay, I want you to go ahead and draw a right bisector of the chord. And that means you need to take that line, find a point that's right in the middle, so that line that bisects it. So it's got a line, the right bisector is a line that cuts this into two pieces, and that means it's got to go right through the midpoint of that line right there. And if I have like something like a sheet of paper, I can just put it along the line, and that way I know that this is 90 degrees, and I can just draw that right bisector just like that. All right, so this is my chord. This is the right bisector. It's certainly a 90-degree angle. Now, what do you notice? Pause the video and examine this diagram for as long as you need. Well, one thing you should ideally notice is that right bisector probably goes right through the indentation you made when you were drawing this circle with the compass right at the center. And in fact, this is absolutely true. The right bisector of a chord will always pass through somewhere along that line is the center of the circle. In this lesson, we're going to learn how to use analytical geometry to confirm some really neat ideas with geometry, to solve some problems that we may face in our lives when the shapes that we're working with aren't really nice regular shapes. To start off, I'd like you to take a look at this problem here. Joyce is buying a triangular plot of land to farm corn and soybeans. Relative to one corner of her plot, the other two corners, remember this is a triangle, so there's 3 corners in total. The other 2 corners are 2 kilometers away on a bearing of north 60 degrees east and 1.5 kilometer away on a bearing of south 30 degrees east. And she wants to split up this land evenly by creating a boundary between, I guess, the two fields, the corn and the soybeans. Where should she create that boundary between the different crop fields? Now, this is a really tough question to even begin to tackle. So before I ask you to go ahead and try it on your own, I'm going to at least help you draw a diagram that describes this situation. So I might say, okay, if I'm looking at a map of this area, right, where we've got north, south, east, and west in that direction, one of the corners that Joyce has on her triangular plot of land, I'm going to put it right at the center because the other 2 corners are sort of relative to where this corner is. So if I put this at the origin, I can say, okay, if I'm going north 60 degrees east, right, 2 kilometers away from this on a bearing of, so from here, looking northwards, if I rotate 60 degrees towards the east, and then I go 2 kilometers in that direction, I'll find the other corner. So I'll put a point right there. I'll label that point B. And then very similarly, if I go from south, if I go 30 degrees towards the east, so just like that, rotating 30 degrees this way, and I go 1.5 kilometers in that direction, I'll find the other corner, and I'll label that point C. And just like that, I've got a diagram of Joyce's triangular plot of land. If you can pause the video here, try your best to figure out any measurements of angles or side lengths that you possibly can that are not already labeled for you here, and resume the video when you're done that. Okay, let's tackle this as best as I can. So first of all, I've plotted these points on a coordinate grid here, but I haven't really specified what X and Y are. So I'm going to do that now. Whenever you're starting a word problem, it's always a really good idea to define your variables. So I noticed that, as the x-axis increases, we're moving further east. So I'll say, let x represent the distance east from the first vertex, and the unit that will be in is kilometers. And y will be very similarly the distance north in kilometers from that first vertex. Now, if I want to find the boundary that she should create, I really want to know the exact locations of these points here, right? Whenever we're doing analytical geometry, it really helps to find the vertices of our shape. I know that A is at 0, 0, obviously, but how can I find out the coordinates of B? One way to do it is to take this side right here and imagine that this is the hypotenuse of a right-angled triangle. If I were to do that, the bottom side here, so that's this side over here, would be the exact coordinate of x. The x coordinate of this point right here, right? X is a measure of how far we're moving to the right. And so the x coordinate of point B would just be this side right here. And the vertical side here, well, that would be the y coordinate. And I can use this idea to, and the fact that this is a right triangle, to start solving all sorts of things. Now, I'm not sure if you recall very much about trigonometry, but you can solve a triangle if you have 3 pieces of information. Right now I have a side length, and I have one angle measure, and I need one more piece. And that part is actually kind of easy to find as well. This angle right here is 30 degrees. And I know that because this angle is 60 degrees, and I know that north and east make a perfect 90-degree angle, or right angle, between each other. And so 90 minus that 60 means that this resulting angle right here, this one right here, is 30 degrees. All right, now that I have three measurements about this right triangle, I can actually solve the entire triangle. Because I only have one side length and I have an angle measure, it's time to break out the trig ratios. So I'm trying to solve for the x and y coordinate of point B. And so this side, if I have this angle measure as 30 degrees, this side is the side that is adjacent to the angle measure, and this side is the side that is opposite it. And now that I know that, I can actually use the sine ratio if I want to find. The sine ratio is the opposite to the hypotenuse, right? This is the opposite side, YB. The hypotenuse I know has a length of 2, and the angle here is 30 degrees. And so I have an equation. I replaced all of the variables except for one, and now I can actually isolate that variable to find out its value. I'll just multiply both sides by 2 to do that. And that gives me 2 times sine 30 equals the y value of b. And 2 times sine 30, if you put this into your calculator, you'll get exactly 1. Sine 30 is equal to exactly 0.5 times 2 is 1. And actually, in my diagram, hey, that actually tracks. Yeah, my diagram was pretty good. I put the point B, its y value was just at 1. To find the x value, I have this is the adjacent side, and the ratio that compares the adjacent side to the hypotenuse is cosine. And so cosine of 30 degrees will be the value of x divided by 2, the hypotenuse. Once again, I'll just multiply both sides by 2. Now, cosine of 30 is not a nice number like 0.5. Cosine of 30 is actually a radical number, which is root 3 over 2. And root 3 over 2 times 2 is exactly root 3. If you put this into your calculator, some calculators are capable of taking large expressions and giving you an exact number expressed as a radical or expressed as a fraction. My calculator was pretty good. It gave it to me as a exact radical. And so all of this work was done to find the exact coordinates of B. And that's going to be at root 3 and 1. I can do the exact same steps actually to find the coordinates of C. I can say that, okay, let's say this is the x value, this is the y value, that makes a right triangle. And using this right triangle, because I know the hypotenuse, this side is this angle, excuse me, is 60 degrees, because 90 minus that 30 got me 60. And now I can use the exact same steps here. Sine of 60 is equal to the opposite over the hypotenuse, and that's multiplying both sides by 1.5. I'll find out that 1.5 times 60 will give me the y coordinate of point C. The problem is this is not a very pretty number at all. Sine 60 is also equal to actually root 3 over 2. And if I want to multiply that by a decimal, I won't really get a really nice number. But and I'm going to be skipping a lot of steps here in how I'm getting this answer. Your calculator will give you a number that's probably a mix of a fraction and a radical. The exact value of the y coordinate of point C is the square root of 1.6875. And again, this is not necessarily something that you may be able to come up with yourself at this point, depending on which skills you've practiced so far. But certainly your calculator will be able to, should be able to give you, if you have a scientific calculator, it should be able to give you an exact value. And we're just going to say that that is the value of the y coordinate of point C. I can use the exact same steps here to find the x coordinate, right? So that's cosine of 60 is equal to the x coordinate of point C divided by 1.5, the adjacent divided by the hypotenuse. If I multiply both sides by 1.5, cosine of 60 is actually equal to 0.5, and 0.5 times 1.5 is 0.75. And so I found the coordinates of B, and I found the coordinates of C. Now that we've got that, actually a lot of the hard part is out of the way. I wonder if you can take the reins from here. So now that we've got all three of these coordinates, do you think you'd be able to find the boundary that she should make to evenly split up this triangle into two sections, one for corn and one for soybeans? Pause the video here and try your best to take a crack at that. All right, well, hopefully one thing you recognize is when we want to divide a triangle evenly, the one way to do that is to draw a median. A median bisects a triangle's area always. And I'm just going to draw mine from the point A, although certainly you could draw a median from point C or from point B. For me, from point A going across to the midpoint of the opposite side, that's exactly what a median is, right? And because it's the midpoint, it cuts this side exactly in half. So this length is the exact same as this length. And this area, therefore, will be the exact same as this area. They both will have, it'll be a really even split in between corn in the top, maybe in soybeans in the bottom. And all we have to do to help Joyce out here is to communicate the exact point of this midpoint, right? Or the exact location of this midpoint, excuse me. And the midpoint between B and C can just be found by averaging the x coordinates and averaging the y coordinates. And now that I know all of those coordinates, I could just plug those in to the appropriate areas. And if I put this into my calculator, I get an approximate answer of 1.241, and of course there's more decimals afterwards. And if I put this in, I get about 1.1495, and of course still there are more decimals afterwards. But I think for the purposes of this, I'm just going to call it right here and say to Joyce, hey Joyce, if you want to make a boundary, you can start at the first corner here, and the end of your boundary should be, well, the x coordinate here, 1.24 kilometers east of the first vertex. and the y coordinate is about 1.14 kilometers south of the first vertex that she's got right there. And that's exactly where she should create her boundary. 1.24 kilometers east and 1.15 kilometers south of the first corner. So in this lesson, we've learned a couple things. The first thing is what a chord is. And remember, that's a line that connects 2 points on the circumference of a circle. And a chord is pretty important for analytic geometry because the right bisector of a chord goes right through the center of a circle. And that can really help us find the center there. If we're solving problems with analytic geometry, we also saw in that example here that there's many steps you may have to use to do it. And these steps are not really steps that I can always, that I can give you sort of an algorithm to always execute for every single one. Every single one is different. But here are just some tips to help keep you on the right track. First, definitely read the problem as carefully as you can and try to understand what it's asking and what information it's providing. It will always help, in my opinion, to draw a diagram and on your diagram label any measurements that you know for certain to be true. In that diagram, if you have introduced any variables, definitely define what those variables are and please include the units for that. And for example, let x represent the distance between these 2 points in centimeters. Once you're done that, hopefully you understand the problem really thoroughly. Then from there, here's really the hard part, the part that can't really be taught too well and takes a lot of practice to do this. But you got to just make a plan. Figure out how to get from your known quantities to your answer, and then write down the steps of your plan. Once you're done that, carry out your plan. Make sure to keep all of your work really organized as you do so. If you notice, I love to color code things so that I know exactly which value I'm referring to. And while you're carrying out your plan, it's pretty critical that you do not round any values during that process. And that way your final answer is kept as exact as possible. As you find new and newer measurements, add them to your diagram and just check while you're doing that to see if they make sense. Maybe you missed a negative, or maybe you added instead of subtracting and you ended up getting a number that's bigger than it's supposed to be. If you add that measurement, that new number that you found, to your diagram, it should immediately be obvious to you if it's too big, or if it's negative, or it should be positive, or if there's some sort of problem with it. Finally, once you're done carrying out your plan, add a final statement that summarizes what you've learned, and at this point, you can round any value you'd like to whatever you feel is appropriate. Here, Dustin is trying to find the secret location of Robin's radio tower. Now, he notices that his radio loses signal at the following locations: Starcourt Mall, Castle Byers, and Hawkins Lab. And so if we want to find out what that secret location is, actually we have enough information here to use analytical geometry to tackle that. Pause the video here and see if you can use the things we learned in this lesson to find the exact location of Robin's radio tower. Well, as I endeavor to do the exact same, keep in mind that your first step should always be to define some variables that you're planning on introducing. And I think there's 2 things that I'm going to introduce here. I'm definitely going to plot these points out on a map. And on my map, the x value will represent the distance east from Dustin's house. So all of these are sort of measurements or values of x, with 4 actually being -4 because this one is going in the other direction of the other 2. And y is going to represent the distance north, and these will be my y values, except these 2 are negative because they're not going north, they're going the opposite direction, south. And so if I were to plot this out on a little grid here, these are my 3 points. Right here is Starcourt Mall, here is Castle Byers, and here's Hawkins Lab. Now, How does this help me? Well, the reason he's losing his signal is because he's leaving the range of the radio tower. Radio towers can only broadcast a certain distance, right? But that distance should theoretically be the same in all directions. So all of these points should be the edge, the limit of the radio tower's distance. And that should be a circle with a radio tower somewhere in the center over there, right? Now, how would we find the center of a circle? Well, one way I can do it is by recognizing that the center is always going to be at the sort of the concurrency point of the right bisectors of a triangle. That's one way to tackle it. Another thing, and this is one way that we actually looked at in this lesson here, is we can draw, if we connect the points on the circumference of a circle with chords, just like that, then draw the right bisectors of those chords. They will go through the center. And I only need two of them to go through the center to sort of triangulate exactly where that point is going to be. Both those right bisectors will intersect at one point. All right, so the my plan here is to definitely find the right bisectors of at least two of these lines. And then find out where those two right bisectors intersect, because that will be the center of the circle. And so let's go tackle this one step at a time. So for the right bisector of AB first, to find the right bisector, I need the slope and the y-intercept. The slope's pretty easy to find. It's just the negative reciprocal of the slope of A and B. So the slope of A and B can be found by taking the rise divided by the run. I'll subtract their y values, I'll subtract their x values, and before you know it, that's what I got. That's the slope between A and B. Of course, a negative divided by negative will make this entire number positive, and therefore the right bisector will be the negative reciprocal of this. So the right bisector will certainly be a negative number, and it'll just be the reciprocal of this. So I could just flip those to make 2.06 the numerator and 14.88 the denominator. Now that I know the slope of the right bisector of AB, I just need to find out the point that it goes through, and because it bisects AB, it should go right through the midpoint. And the midpoint can be found just by averaging the x values and averaging the y values. So if I do that, I'll find the midpoint is right at 12.91 and 4.77. The last thing is I need to find the y-intercept, right? I have the slope of the right bisector. I need the y-intercept, which is b. And to actually find b, I need the other two values, x and y, and now I actually have those because that's the midpoint of a and b. Just to isolate b, I'm just going to do it algebraically first without substituting anything in. To isolate b, I just have to subtract mx on both sides. That will get rid of it on this side, and then y minus mx will be on the left, which is exactly what I've got here. Okay, so b equals y minus mx. My y value is 4.77, m is negative 2.06 over 14.88, and x is 12.91. Now here comes a bit of a tricky part. It was pretty easy for me to average these two and just get an exact value. But once I start dividing numbers that are both decimals, especially like 2 decimal places, and then multiplying that by another 2 decimal places, the number is going to get kind of ugly. So I'm just going to put all of this into my calculator and let it give me an answer. And then there should be a button on your scientific calculator to change the answer into its fraction form, which is exact. And I did that with my calculator, and I got this expression right here. Now it's a pretty big, pretty ugly fraction if I do say so myself, but this is the exact location of the y-intercept of the right bisector of AB. And let me start to put these numbers here in context on my diagram. So between point A and B, the midpoint is right over here. And I can see that, yeah, 12.91, that's falling right on my, on my diagram. That's falling exactly where it should. And 4.77, yeah, well, it looks like it's kind of at 5 instead. Maybe I should have moved the midpoint down a little bit, but I think this is pretty good, especially for just being a sketch. And the right bisector is going to look like that. Now, certainly, it's going to meet this at a right angle. It's going to cut this into two equal pieces. Another thing to note is that the slope here is negative, and certainly I calculated it to be a negative number. And it's also a pretty flat slope. And of course, my numerator, the rise, it's only going down by 2 every time it goes across by 14. So this looks pretty close or to what I had calculated it should be. Finally, the y-intercept looks like it's about, if I divide these two, I should get a number that's about 7. And in fact, if you want to try that out yourself, you should get 6.55 is the approximate value of the y-intercept. And it looks like it's going, maybe it might be a little bit high, probably because this guy's a little bit too high, so I maybe could have moved him down a little bit. But that's all right. So that's my sketch is pretty good so far, at least. I know the exact values, so I don't really have to worry about my sketch being off a little bit. Moving on, that's my right bisector. So Robin's radio tower is at the center of the circle, and this does go through the center of the circle, so it's somewhere along this line. But where exactly? Could it be here? Could it be here? Could it be here? Somewhere. For me to figure out a little bit for me to get the exact value, I think I would need another line going through this, and that's the right bisector of B and C, of BC. So BC, again, I'm just going to follow these exact steps to find the equation of the right bisector, right? So that is the slope, rise over run. The right bisector slope is going to be the negative reciprocal of what I calculated, the slope of BC to be. And I'm just going to use this exact same pattern again. The y-intercept of the right bisector can be found by taking any y value and subtracting the slope times the x value of that point. I don't have a point yet, but of course I know that the right bisector is going to go through the midpoint, and I know how to calculate the midpoint as well. So that would be at 3.94 and negative 5.535, and these are exact values. And does that look about right? Like the midpoint should be about here. Yeah, that's 5, so 3.94 looks like a really good x coordinate. Negative 5.5, yep, that's negative 5 right there. So those two values look like they make sense to me. I'm going to take those two values, plug them into x and y, take the slope, plug it into m, and evaluate all of this. And very similarly, I will get a really big fraction here. If you were to divide these, you'd get about 5.38, but I'm going to leave it here because this is an exact number. Again, my calculator is able to convert any answers into their exact value most of the time, at least. And does that look about right? Well, let me draw that right bisector. So, that's the coordinates right here, 3.94 and negative 5.535. The right bisector looks something like that. And does that look like it goes through 5.3? Not exactly. It probably should be a little bit higher. Maybe my sketch is a little bit off here. But that's generally what it should look like. With the line crossing my other right bisector, both of these lines go through the center of the circle, and that they only cross each other. They only have one point in common, and that's right there. So that must be the location of Robin's radio tower. So now we've got the slopes and the y-intercepts of both right bisectors of the chords, which means that we can turn these into the actual equations of those right bisectors. So here we have the right bisector between A and B, and here we have the right bisector of B and C. Looking at our diagram, we can see that they both intersect at only one point, right over here. And if both right bisectors of chords must go through the center of the circle, well, the only point that they have in common must be the center of the circle. And it actually looks like that too on my diagram. And so that's right over there. All we need to do now is to find the point of intersection. And to do that, I could just take the equations and make them equal to each other, just like that. And so if this represents the y value, and this represents the y value as well, well then the only point, that point right there, right, if this equation helps us find the y value and this one helps us find the y value, then this x value must be the x coordinate of this equation right here. And we can find out what that is now that we have an equation with only one variable just by isolating x. So I'm going to add, because this is negative, so I'm going to remove this term. I'm going to move all my terms that have an x to the left side. So I'm going to do that by adding 2.06 over 14.88 to both sides. So you can see I've got that here. At the same time, I subtracted 617,033 over 114,600 from both sides, and that moved it over from the left side to the right. Now I'm going to actually use my calculator to add these two coefficients of x together. At the same time, I'm going to actually evaluate this right side as well. And again, my calculator is the one that's able to give me this answer as an exact fraction. I'm not actually going to go ahead and do all that work myself. Finally, I'm going to divide both sides by the coefficient of x because this is being multiplied. So obviously I do the opposite to get rid of it, which is division. That will get rid of the left side. And when I take this and divide it by that fraction, my calculator gives me the exact x coordinate of the point of intersection. This is an exact value, and it's approximately equal to negative 0.445. Remember that the whole point of me doing all of this is to find the x and y coordinates of Robin's radio tower. So now that I'm at the end, it's not a bad time to actually think about rounding my values, because this is my final answer. Of course, I still need a y coordinate, so I'm actually not going to use the rounded version of my x value. I'm going to use the exact value right here. And I'm going to plug that into, I could actually put it into either line if I want, but I'm going to actually use this line right here for no particular reason. I'm going to plug x into there and then find the y value by evaluating this. And again, I'm just going to throw that right into my calculator and it'll give me this fraction right here. And here's its approximation. All right, well, now I've got the x and y approximate values, at least of Robin's radio tower. And when I plot those on my diagram, you can see right over here I've got that. Let me just check if these values make sense. So negative 4.45 looks a little bit closer to like maybe negative 2. But of course, maybe my sketch was a little bit off. The 6.618, this looks a little bit closer to 7.5, but again, same reason. But they are pretty close to the location that I was expecting them to be. And I do trust all of my calculations were correct. So this must be the coordinates. Our last step in any word problem, of course, is to interpret our answer. And of course, at the beginning, I defined my variables. I know what x and y represent: the distance east from Dustin's house in kilometers, and y is the distance north in kilometers. And so Robin's radio tower must be 0.445 kilometers to the west, not east, because west is the opposite direction, and 6.618 kilometers north of his house. And in finding those, we've helped out our boy, Dustin, and he knows exactly where to find Robin now. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.